Hello folks, how you doing today? It's been quite a while. Over here we are presented with another fascinating mathematical video. But this time around we are considering problem from analysis and it's a limiting problem. Alright? I would like to add that I offer personal or private online tutoring. So if you're interested in online private tutoring, be very free to get across to me by my email I provided, or you can click the link and you take it to my Telegram, whereby we can have a detailed conversation on how the online class should be. That is an arrangement of how it should be. So if you're interested, I'm a very qualified candidate. I'm competent and prolific in my area. All right. I've been into mathematics for quite over a decade now. A decade now. I've been into mathematics. All right. So if you're interested, you want a one-to-one tutoring, you can be very free to get across to me, and I will make provision for that. All right. Now, in limits, or rather in analysis, this definition I gave over here of limits is very important. If you want to grapple with concepts in analysis, this definition, at least you should cram it at least, but it's not advisable you get a cram of it. But if there's no other way you can understand it, do a cram of it, because you can't do without this definition. At least I mean this definition provided here, this over here. Can you see that? You can't do anything aside, you can't do anything apart from it. So you must at least cram this definition in order for you to grapple through uh, with concepts in analysis. All right, very, very important. That is when talking about convergence, derivative, integration, boundedness, monotone increasing function. There are so many concepts that are discussed in analysis. All right. There are other one again. Measure. You must this definition. You must know it. If you don't know this definition, it will be very difficult. I don't even see a possibility of you following through. All right. So if you're interested in a detailed discussion, as I said, you can get across to me. I will make provision for that. Now, this is the definition. Let's look at the definition together. Now, what is the meaning of the limits of the function phi of x equals to lambda? What is the meaning of this statement? That is, what is the meaning of this statement over here? What does it mean? To say this, what is the meaning of that? This thing has come to distort our work. Excuse me. I want to get this out of this place. See. All right. So let's continue the word discussion. So the meaning of this, it means that for all, this symbol here means for all. All right. Let me use this means for all. Can you see that? For all. For all positive number epsilon. All right. For all positive number epsilon, take note of the word for all. That means there is no restriction as to how the positivity of the number should be. It can be extremely small but positive. It can be extremely large but also positive. So we're concerned about positive number in this definition. All right. For all positive number epsilon, there exists, this symbol here means there exists. All right. There exists a positive number delta. This is the data you are seeing here, such that for all x, can you see that? For all x, if this condition you are seeing here holds, that is, if the modulus of the difference between x and a is less or is in between 0 and delta, can you see that? This is it. If this is the case, then this is true. That is to say, this condition holding will implies that this condition over here also hold true. All right. So there must be a condition. In this case, it's a condition involving delta, a delta condition that will enable this epsilon condition to be true. That is what, if this is the case, then we can say that the limit, this statement over here is true. All right. Otherwise, it is not true. So there must be a delta condition that will implies or ensure that the epsilon condition is true. If we can have that, then this statement will be correct. And don't it will never fail. It will be true for all epsilon. That is, this epsilon you are seeing, you can all positive epsilon. It must be true for all. Hence, I laid emphasis on the word for all. All right. So if that is the case, then we can say that the limit of the function holds true. So with this definition, we want to prove the following. Now we're given a problem here. He said if the limit of f of x as x approaches a is m, and the limit of g of x as x approaches a is L, show that the limit of the sum of the functions as x approaches a is equal to the sum of the limits. We are to prove that. All right. So how do we go about the proof? Now, if you observe carefully in this statement, we are given hypothesis and conclusion. The hypotheses are these. These are the hypotheses. Can you see that? Oh, I've destroyed this already. Oh, we'll do this now. Sorry for that. I have to write this again. So, excuse me. So let me rewrite this that was removed. I think also this also. All right. Or then something of this. All right. So we have to show that this conclusion is true if this hypothesis given here is true. Right? Or to establish that. So take note of what we have to establish. So what we do, this hypothesis, let's suppose the hypothesis is true. All right? Then from this supposition, we want to establish this conclusion. Let's do that. That is how to carry out proof in analysis. And also in any other aspect of mathematics, in geometry, we always work by giving hypotheses. From the hypothesis, we establish the conclusion. Now we can say suppose that the limits of f of x as x approaches a is indeed m. All right, let's suppose this. Then it is a well-known thing that then for all epsilon that is bigger than 0, you agree with me that epsilon over 2 is also bigger than 0. Hope you agree with that. Yes, it's very correct. Now listen very well. If we are to take this as a choice of our epsilon, that is this, let me remove this for try to be neat. If we are to take this result, this quantity as a choice of our epsilon, then it should be a delta that will guarantee the above condition. That is over here. Look at it over here. Can you see that? And in this case, the delta condition is this. So there must be a delta such that this condition will guarantee this condition. All right. So take note of that. Very, very important. So let's call that delta that will guarantee this, because now we'll be given that this is true. So if this is indeed true, that means there's a delta that guarantee the above condition, that is this condition here. This where is it again? This condition over here. All right. It's a delta that guarantees it. But in this case, the function was phi, but over here it was f. So we can say then there exists a delta sub 1 that is positive, such that for all x, if we now create a delta sub 1 condition, if 0 is less than x, the modulus of x minus a, and that is less than delta sub 1, then this epsilon condition should be true, which is f of x minus m should be less than epsilon over 2. All right. So if this indeed, this statement, this claim over here, if this claim is true, then this must follow. This must follow. All right. Hope you see that. So we're done with that. So we can say also let the limits of g of x as x approaches a be L as claimed in the problem. All right. Then for all positive epsilon, we know that epsilon over 2 is also positive. Now let's take this epsilon over 2 as a choice of our epsilon. Let's take this. So if we are taking this as a choice, and also if this statement is true, all right. Oh, this has start again. So if this statement is true, I mean this statement, right? If that is the case, all right, so it's not out of place. We are still, this thing is not responding the way I expected it to respond. So if this is true indeed, then there should be a delta that will make our epsilon condition true. All right, so we can say then there exists a delta sub 2. Let's call that delta sub 2 that is positive, such that for all x, if 0 is less than this difference, the modulus of this difference, and this is in turn less than the delta sub 2, then we have that g of x minus L is less than epsilon over 2. Hope you see what I'm doing. Now, let's consider the minimum of the delta sub 1 and delta sub 2. And let's call that minimum delta. That is, we can write consider the minimum of delta sub 1 and delta sub 2, which we call delta. All right. Now, on consider this minimum, if we are to form a delta condition, the delta condition will guarantee the validity of these two epsilon condition, this and this. Here's it again, and this is a very I would like to, excuse me, this again will remove most of our work. I don't want that to be, or to clearly remove. All right. It's okay. Then we have this. All right. So if this condition is true, this is an epsilon condition, right? It's an epsilon condition. We are seeing that now. So as I was saying, this delta condition over here will guarantee this the truths of these two epsilon condition, this and this. All right. So in that case, we can say then for all x, if 0 is less than x minus the modulus of x minus a less than epsilon, then we have that the epsilon conditions are true. Can you see that? So that's the case because we are taking the minimum of delta sub 1 and delta sub 2. So this will be the case. Then also we can also observe, we can consider a quantity. We can say consider the quantity. Let's consider this quantity. Now, as a well-known thing, this quantity we are considering can also be written in this manner. What we see that can be written in this manner, all right? Now, from a triangle inequality, this last statement can be written as less than equal to f of x minus n plus g of x minus L. All right, we have this as a result. Now, don't forget that then we can say that the modulus of f plus g of x minus m plus L is less than or equal to this statement over here. Can you see that? All right. Now, don't forget, let's go back to this our condition again. This is our delta condition we just made. This condition over here. Can you see this condition over here? All right. Now, if this is the case, then we have already said that this and this will be simultaneously true. We said that initially, all right? So on applying this condition, this data condition in this last line, we shall have the following. Then we can say if 0 is less than x minus a less than delta, which is the minimum of delta sub 1 and delta sub 2, then this sum f of x minus m plus g of x minus L will be less than the sum of halves of the epsilon, and that will give us epsilon. All right, can you see that? Because we said initially over here that if this is true, then this and this will be both true. All right, so that means if this is true, the sum of this will be less than the sum of these two halves. All right, so we have these results. So that means, what are we saying in effect? Therefore, we are also saying that if 0 is less than x minus a less than delta, which is the minimum of delta sub 1 and delta sub 2, then we are saying that f plus g of x minus m plus L is also less than epsilon, because don't forget this over here is less than this, all right, and this is strictly less than this. So that means if this condition is true, it follows this will happen. So this is a delta condition that guarantees this epsilon condition, and this epsilon is an arbitrary epsilon, that is for any positive epsilon. So because we obtain a delta condition which is the minimum of a delta sub 1 and delta sub 2 that guarantees this epsilon condition, because we have this at hand, it is enough to say that the limit of a sum of two functions is equal to the sum of the limits. So we can then say, therefore, the limit of f plus g of x as x approaches a is indeed equals to m plus L. And m is what? Is the limit of f of x as x approaches a, all right? Also, L is the limit of g of x as s approaches a. So in this way, we've established the claim. The claim has been verified and it's true. So that means the sum of a limit is the limit of the sum, provided the limit of the summand exists. So that will be the case. So we call it a close for the now. You go through this video once, twice, and thrice for a proper grasp of what I've explained. All right. I repeat again, if you're interested in a online private tutoring, you're very free to get across to me via the email address I've provided over this page, or you click the link also provided and you take it to my Telegram where we can have a detailed explanation, all right? Sorry, discussion and agreement on how the class should be run. So thank you very much. Have your time, enjoy your time. We're done with this particular problem. So till other time.